Hi guys, and welcome to another episode of Technically Speaking. It's good to be back, and it's even better to be back in the seat of an Evo 9. What a car. Today, we're talking about boost control, more specifically, boost by gear. So basically what's going to be happening, we've got our Evo 9 test mule here. This one's actually Davo's car. It was the Mighty Car Mods car. It's a perfect test mule for this because it's got a really reliable 4G63 Evo 9 engine with the MyVec, so the variable inlet cam control. It's got a really nice turbocharger on it. It makes about 280 kilowatts at the wheels, but it can also make 220 kilowatts at the wheels when we're on wastegate pressure. So it runs somewhere between about 18 and 24 pounds of boost. But what we want to talk about today is being able to configure it to have different boost levels in each gear. So what we're going to do is first configure our target boost pressure configuration in the software. And what's going to happen is, as I drop to say fourth gear, for example, the engine management system is going to see that I'm in fourth gear. It's going to see that I'm at, say, 50 or 60 or 70% throttle. And it's going to look up our boost target and say, okay, I know that he only wants 18 pounds there, but when he goes to full throttle, he's going to want 24 pounds, for example. One of the things that we can't do on the dyno is set it up and do full power runs in first gear and second gear and probably third gear on the four-wheel drive chassis dyno. Because of the torque multiplication of the gearing, if we try and do a first gear full throttle run on a chassis dyno, it's not going to end very well. We're going to end up lurching off the front. We'd need a million straps and it'd all be too hard. So I'm just sort of getting a bit of a feel for it now. We'll go back to the shop, we'll get it on the dyno, we'll configure the closed loop boost control strategy, then we'll figure out how we're going to target the boost pressure versus whatever we've got, throttle position versus engine RPM versus gear, even versus this little intercooler water sprayer button here. So I could turn that little button on and I could get all the beans, or flick it off and we'll go back to wastegate pressure. But I am going to have to do plenty of test driving in this car. It's Evo 9 was my first sort of first new car. I bought an Evo 9 brand new and I absolutely love it. I regret selling it. What a beautiful car. The noise of it. Oh, let's see if it's got the beans too. Oh. Ah, what a car. Now there's a whole bunch of different ways you might want to manipulate your boost pressure. You might want to have a target boost pressure versus engine RPM. You might want to have it versus road speed or length of your drag race. You might want to have it, if it's a circuit car, your manifold pressure or your target boost pressure might be versus throttle position, because mid-corner at 40 or 50% throttle, you don't want full boost. Then as soon as the car starts to straighten up and you start to come out of that corner, you mash the pedal, you then go to your high boost, your flat out boost pressure, and it makes the car a lot more controllable. You might want to do something like have a high-low boost switch. In this car, really good example, it's got an intercooler water sprayer off the front of it, which is factory on this Evo 9. It's got an automatic button. You press that, little light comes up on the dash telling you that the intercooler water sprayer is working. Well, not so much about the intercooler water spray. What's important about that is that input goes into the engine management system. That's a channel that's in there that tells us whether the water sprayer is on or off. We can use that channel to map the boost pressure against that. So the driver of the car, if the water sprayer is not on, we might target, say, 20 pounds of boost pressure. If the water sprayer is on, we might target 24 pounds of boost pressure. If you're not lucky enough to have a built-in switch like that in whatever car you've got, you might be able to use like a rotary trim knob. So you could have a 12 position switch that you'd mount somewhere on the dash. You could have position 1 as the lowest boost pressure or the wastegate pressure. You might crank it up to 11 or 12 and that's kill mode. That's as much boost as the engine's going to take, maybe even a little bit more. So the first thing we've got to do is tell the engine management system what gear we're in. So some gearboxes have got a position sensor for each gear or a potentiometer that changes voltage depending on what gear it's got. Some automatic transmissions are CAN based and they send the gear detection system or the gear detection strategy via CAN to the engine management system. Evo 9, the last of the old school mechanical cool Evos, in my opinion, hasn't got any fancy stuff like that. So we need to use a gear ratio detection in order for the engine management system to know what gear we're in. It's pretty straightforward. All we do is cruise the car in first gear. We go to our gear ratios tab on the left-hand side here. Then we come up to this button here. What's going on here? I've already configured this, but what's happening here is, so 9.1 is what we detect as our gear ratio for first gear. So that means that we're going 9.1 kilometers per hour per 1000 RPM. So if the clutch is out and we're truly engaged in first gear, the engine management system will know that we're in first gear, because that relationship between engine RPM and road speed only changes when we change gears. The first thing that we'll need to do, the boost control target pressure. This is where we're going to make the decisions on how the boost control target works. So at the moment, you can see that this car is configured so that if the intercooler water spray is turned off, it targets 18 pounds of boost pressure. If the intercooler water spray is turned on, it targets 23 pounds of boost pressure. It's also mapped the second table axis versus engine RPM. So at no matter what the engine RPM, it's always targeting the same boost pressure in this case. So I can change that straight away. All I'm going to do is press F3 or go to the setup table options. And I'm going to change this around a little bit. So I'm going to set it up so that we've got engine RPM on one axis. I'll set it up so it's got throttle position on the other axis. Being an Evo, it's nice to have a bit less power when we're at light throttle. And then you'll notice that I did lose my intercooler water spray set up down the bottom there. So I'm going to enable down here. We could map it versus fuel composition. So that's a very common thing. So say if the thing was running on petrol, it might run a lower boost pressure. If it's running on E30, we might add a little bit of boost to it. E50, a bit more. Once it's on E85, we'll run as much boost as we possibly can. In this case, I'm going to change this to intercooler auto input state. And we're going to either select it as a 1 or an on. Or an off. If I press OK, what we'll see down the bottom here in the software, all of a sudden that little bar has turned up down the bottom. So if the intercooler spray is turned on or turned off, I'm pressing the button at the moment and we can see the little indicator down the bottom. It's on, little blue arrow over here saying it's looking at this map. Off, it's looking at this map over here. If I pull that little scrolly bar across, what we better do, so if the intercooler water sprayer is off, let's put it at say 18 pounds. If it's on, let's put it at 23 pounds. That makes it nice and easy and we can flick back and forward and see how that's working. So this car has already been tuned. Remembering this was one of the Mighty Car Mods cars that got done a couple of years ago. Since then, Davo bought the car. He loved it that much. He's been daily driving it. It makes about 280, 285 kilowatts at the wheels and everything's been going really, really well. We're using it for the demonstration here because the boost control sort of configuration and setup on this car works really well for an example where we can increase the boost 2 PSI at a time and see what that result is. This car's got an 18-pound wastegate spring, meaning that with no electronic intervention, it's going to run 18 pounds of boost pressure. So for the examples today, we'll go up here, we might target, say, up to about 24 pounds of boost pressure. But like I said before, at lower RPM and lower throttle positions, we might not want to run as much boost pressure in order to make it drive a little bit nicer and be a little bit more controllable mid-corner. So I might go here and run 18 pounds of wastegate pressure up to say or up 18 pounds of boost pressure, I should say, up to 40% throttle. Then I'll go across here. I'm going to go L for linearize to smooth that across, and down low in the rev range as well, just to not give it such a hard time. We might go L for linearize and end up with a boost map, something like that. You can choose all different ways to do it. If it's a street car and you want unlimited power all the time, just put one target number. Remembering the whole purpose here, you can map it against anything you want. Engine protection wise, if the car goes into engine protection, we can also change the target boost pressure so that if it's a light engine protection warning, so something that's not critical and that's not going to turn the engine off to save it, we could choose to say pull half or as much boost pressure out of it as we can. And we could also set a boost limit based on that engine protection. We did gloss over a bit of this stuff in the R35 boost control video. I'll go through this in a little bit more detail in this particular video because it's all well and good to tell you, yep, you type in the boost pressure and it achieves it, and that's as simple as that. But it is a little bit more complicated. Like everything in cars, it's always going to be a bit more complicated. This is a closed loop system, and what that means is that the engine management system is looking at the manifold pressure, it's looking at the target, then it's doing a whole bunch of magic in between in order to pulse that solenoid more, less, bleed a bunch of air off that solenoid in order to achieve the target. And how it does that, well, it's pretty impressive, but it does need a little bit of input from the tuner to help it get there. The more input the tuner gives it, the more accurate the boost control is going to be. Starting from the top, the closed loop base duty cycle. If I have a look across here, this has got my target boost pressures. So that top axis is based on my closed loop target pressure. If I was targeting 20 PSI of boost pressure at 2000 RPM, before we go into any closed loop or any strategic boost control strategy, the engine management system is simply going to start pulsing that solenoid at 19% duty cycle. It's going to do that before it even comes on boost. Before anything happens, it's just going to think, that's a start position, I'll start there. It's going to keep pulsing that at that duty cycle for 2.5 seconds, our delay, or if we were at 4,000 RPM, for example, it'd be at 1.5 seconds. Once that delay finishes, the engine management system is then going to look at the target pressure versus the actual pressure, and it's going to drop into its closed loop strategy using our PID, our proportional, our integral, and our derivative controller. Now, this is a pretty complicated topic. I'll do my best to sort of explain it in a couple of words. We will do a future video on PID control stuff with a few more examples to show you how sort of things are working in any of the closed loop strategies, whether they're boost control, idle control, O2 control. So anything that's got an actual pressure and a target pressure, it's using a closed loop system and it's using a PID controller in order to achieve that target. Once we've got our target of, let's say, 20 PSI, we already know that we said, we'll guess about 19% will get us to that target. Let's say that 19% only achieved 19 PSI, not 20 pounds. That's where our proportional gain comes in. It's going to look at the actual boost pressure. It's going to look at the target boost pressure. Well, we're out by 1 PSI in this example of 19 to 20. Because of the number I've put in here, 0.69, that means that the proportional portion of the closed loop strategy is going to increase our output duty cycle by 0.69% per PSI of error. So I'm out by 1 PSI. It's going to add 0.7, close enough, 0.7% of duty cycle to our output for that 1 PSI. That should bring it up. Once we get up and we have no more error, the proportional part disappears. But then we would fall back down, right? And we would be back down at 19 PSI because we've got an error again. That's where the second part of the formula comes in, the integral controller. What happens here is that once our proportional comes up and gets us to the target, proportional is based on the target error. If there's no target error, there's no proportional. Think of that sort of the proportional like what's happening right now. The integral controller's job is to sort of look at the history of what's been going on. So if we required more duty cycle in order to meet our target, the proportional is there to say, okay, and just keep a rolling tally of what's going on. It's also in output duty cycle per PSI of target error. But when we meet the target, the integral has already kept a running tally of what's going on. It's sitting in the background there, and it just adds that 1%, and it just keeps that 1% so we stay on target. Then we've got a derivative gain. Typically not used as much as the proportional and the integral part of the PID strategy. The derivative, think of it like we're sort of future-proofing what's going on. If the manifold pressure is rising at such a rate that we know that it's going to overshoot the target by a mile, simply by looking at, for example, if we're trying to achieve 19 pounds of boost pressure and the manifold pressure is accelerating at 10 pounds per second, for example, the controller can look at that and say, hang on, that makes no sense because in not much time at all, it's going to accelerate straight past the target. That's way too aggressive. That's where the derivative controller will step in. It'll pull some duty cycle out of the system in order to get us to not overshoot the target. So that's proportional, integral, and derivative. Proportional, what's going on right now. Integral, sort of looking at the history of what's been happening, and the derivative, looking into the future to make sure that we're not getting too carried away. This is a huge topic. There's a million different ways to explain this. I'm going to think of a better way to explain this on the bench, maybe with some balancing beams or some remote control helicopters or something like that. But if that gives us a really basic idea of sort of what's going on in that area, and at least gives us some units to look at so that we know when we're typing in a number of 1 or 2 or 3 in the NSP software, we get an idea of what's going on and what the system's doing. But remembering, in life, we don't want to keep making the same error over and over and over again. Makes no sense. Same in your engine management system. So if we had set our base duty cycle correctly for every temperature situation, every engine situation, we wouldn't need any closed loop stuff because you'd ask for the target, it'd go to that base duty cycle and it'd just work. But engines are difficult, life's difficult. The duty cycle does change on temperatures, on operating conditions, and that's why we've got that closed loop strategy there. So you can get it in the ballpark with your base duty cycle table, then the closed loop will come and fix up any little mistakes. If the closed loop keeps picking up the same mistake over and over again, we've got this next value here, the long-term trim table. So if we look over here at our long-term trim tables, we've got a bunch of stuff we've got to enter. First of all, we need to be over 80% throttle position in order to start the learning. That's because at light loads and part throttle on boost, we're not going to get a consistent result because there's a restriction in the engine, being the throttle blade, that's continuously changing that manifold pressure. We want to be above 2,500 RPM because under 2,500 RPM, it's probably too laggy to actually come on boost and make that full boost. So we would end up, the controller would just keep learning and learning and learning, but could never actually achieve it. We've got a maximum RPM. In this car, I'm going to change that to 10,000, something we're never going to get to, and I just want it to keep learning as much as it possibly can. The minimum gear, we have to be in third gear or above. In first and second gear, because of the ratios, because it's so aggressive down there, we've got such a high engine RPM and manifold pressure rate of acceleration that any learning there is probably going to be null and void. Then down the bottom here, we've got a couple of buttons. We could either reset it, so we'll just clear all of the learned data, and apply to base table. I'll come back to that in a second. We've got our long-term trim gain. So this is a number that basically is asking us, all right, how aggressively do you want this thing to learn? At low boost pressures and when we've got not very much target error, we don't want it to learn very much. If we're a long way away from the target, we want it to learn very aggressively. So I'll change this to numbers of maybe 5 or 10 when we're pretty close to the target, and 50 or 100 when we're a long way away from the target. The long-term trim table. This is the one that fills in and tells us how far out our base duty cycle was. So if we were out, I'm just going to say along here, say our target of say 19 pounds, the closed loop strategy might decide, okay, it actually needs 2% extra there, and it might need 6% or 5% extra there. And for example, that might be some learned data that it would pick up, something like that. The engine management system will look at those numbers. It will add them to the output from the base duty cycle table, and that will be the result that goes to the boost control solenoid. Remember before how I said that I would come back to the apply button? Well, if I press the apply button here, it's going to take all of those learned values, it's going to put them into our base table, then it'll put the learned values back to 0. So you can tune the car, you can send it out on the street, it can do a couple of days, couple of weeks, months, years, whatever. When the car comes back, we can actually use this as historical data as well, because we could look at this and say, oh, okay, well, it needed to add a bunch of duty cycle there. Either I was having a bit of a lazy day and kind of near enough's good enough, which is obviously never the case, right? Or maybe the thing's lost efficiency. Maybe something's going on where we need a hell of a lot more effort into that boost control in order to achieve the same target boost pressure. So have we got a wastegate problem? Have we got a boost leak? Have we got something else going on? So you can look at this and see historical data. It's really useful for that, as well as maintaining our target boost pressure. All right, before we go and give this thing a power run, and we'll do a couple of different power runs at a couple of different boost pressures, I just noticed that this video is called Boost by Gear. When I was setting up the target boost pressure table, you're probably confused because I set it up versus throttle position, engine RPM, and whether the intercooler switch is on or off. So I'm just going to quickly flick down to RPM, and I'm going to change that to gear. That's our calculated gear. I'm going to delete out all those crazy numbers, and I'm going to go first gear, second gear, third, fourth, fifth, being at Evo 9, it's a 6-speed. Okay, done. Okay, so there we go. So now in my table here, I've got gear versus throttle position versus whether the intercooler water sprayer is turned on or turned off. So, whoop, and there's the manual sprayer right there. So everything's working. What I better do, I'll do a base run with 18 pounds of boost pressure as the target, so we get a baseline so we can watch the duty cycle output and see what's going on. I'm going to come down here to the data logging section of the Elite Series ECU, and I'm going to add all of our boost control channels so that I can do some onboard data logging to the ECU. I'll give it a pull, then come back, pull the data out and see what's going on. Within the software here, we've got 3 sets of channels. We've got 20, 40, we've got 60 channels that we can data log, all at different sample rates, anywhere between once every 10 seconds to once every 5 milliseconds. I've also got it configured so that the onboard data log is going to turn on when we go over 3 pounds of boost pressure. And then when it comes back under 3 pounds of boost pressure, it's going to keep logging for 1 second and then turn off. One of the beauties about this software package is that the engine management system, all the Elite platform now do the loop data logging, meaning that there's 8 megabytes of onboard memory on the Elite 2500 series ECU. That's what this car's got in it. That means that it's always going to be logging. We're always going to have the last 8 megabytes of data. Once that at 8 megabytes fills up, it's going to start overriding the old data. So we've always got the last 8 megabytes. Right, so that's all the theory out of the way. Now it's time to give the thing a few pulls and we'll see how this works in practice. So the first thing I'm going to do, I'm going to target 18 PSI everywhere. I'm going to do a pull in 4th gear. Watch what power it makes. Then I'll bring it back to idle. I'm going to go up to 20 pounds. Give it another pull. Up to 22 pounds. Another pull. Up to 24 pounds. Give it another pull. We'll look at what power level it makes each time we increase by 2 pounds of boost. Then we'll pull the data logs out and have a bit of a look at how to compare all of those and make sure that our target pressure is meeting our actual pressure, make sure that all of our duty cycles look good and our long-term trims are working well. Then all we'll need to do is configure what boost we want where. And she's still got it a few years later, over 280 kilowatts of the wheels in this Evo 9. You'd tell I'm excited. I started tuning in my Evo 9. Geez, I love these cars. I might try and get this one off Davo. But back to the story at hand. We just did a power run on 18 pounds, on 20 pounds, 22 and 24 pounds. If we look over at the dyno screen, we can see that each boost pressure made corresponding power increases of sort of roughly 20 kilowatts per 2 psi or roughly 10 kilowatts per 1 psi. That's telling us that the engine's healthy and happy. The turbocharger's got plenty of huff left in it, leaving it at about 280 or 285 kilowatts. Fantastic, the thing will drive great. Down the bottom there, we've got our air-fuel ratio. So that's the one that's in the tailpipe of the car. That's coming off the mainline dyno, independent of the Haltech wide beam controller that's in the car. Nice to have two when we're tuning. And sometimes the car simply doesn't have a wideband in it, so it's nice that the dyno's got one. On the right-hand side there, we've got our independent manifold pressure sensor. So that's T-pieced into the inlet manifold of the car. It's measuring our boost pressure. So if we look over to the right there, we can see that we've got the red one, roughly 18 pounds there. The blue one is telling us 20 pounds. The purple one is 22 pounds. And the green one is 24 pounds. I'm going to pull some logs out of the engine management system. We'll talk about the 24-pound run. It's probably the biggest and most exciting one. But looking at the graphs on the dyno there, I'm really happy with how that's come out. It's almost the perfect demonstration. Coming back to the engine management system, I'm going to go up the top of the page here. We're going to click on the data log manager. It's been logging to the ECU, so now I'm going to extract those logs so that I can view them in the data log viewer software. So we'll cruise down here and go, okay, that last log just there, open in data log viewer. I won't open it there. Okay, she's away. So if I bring up our engine RPM, I'll bring up our manifold pressure. I might display that on a new trace. And that's showing us that we had 24 pounds, perfect, and our boost control target pressure. I'll zoom in on that little bit there. Okay, so this shows us our power run. So as the thing comes up on boost, it makes full boost at about 4,500 RPM, something like that. Then sits right on our target. We've got about 0.3, 0.4 psi of target error. So I'm not even going to worry about it. That's perfect. If I come up here and I'm going to open this one and go our boost control output and our boost control base duty cycle. Now, as it came up, it came on boost. It sat at 33% duty cycle on the solenoid for the start delay time. So that means that it held at my my educated guess, or after doing a bit of experimenting, realizing that it's going to need about 33% duty cycle in order to obtain about 24 pounds of boost pressure. It sat on that start duty cycle. Then when it fell into the closed loop strategy, it started pulling a few percent out. It's gone back to 31, back to 30.7% duty cycle by the end of the power run. So we can see that there, and we've got 30.9% to achieve 24.2 pounds of boost pressure at 7,200 RPM. What I wanted to show you is what the PID controller was doing. So the proportional affects the output, the integral affects the output, and the derivative affects the output. So let's bring one up. Proportional output. How much work was the proportional doing to the output in order to achieve that target? And you know what the truth is? It did very, very little because our start duty was so close in the first place. It's pulling out throughout the run 0.4, 0.5, under 1%. But because we're so close to the target, and remembering that proportional is percent based on the target error. So if the target error is 0, our proportional is going to fall to 0. If I bring up our integral output, we're going to see by the end of the run, so remember that's the historical value. So that's looking at sort of, not cumulative, but it's looking at what the proportional has needed to do in order to achieve the target, and kind of keeps that rolling average so that Once the proportional drops away, the integral is there to hold the target. If we cruise along here to the right here, we're going to see that in order to achieve our 22 psi, by the end of the pull, our integral is pulling 2% out of that base duty cycle. So that means that we've got 2% integral is getting removed. We've got 0.2% of proportional. That's 2.2%. Our output in total, let's say somewhere there. So what should happen here is we should end up with, we've got what I thought was going to be 33% minus 1.9% minus 0.1% results in 31%, the actual output required in order to maintain that target boost pressure. There is our P&I in action. That's how it's working. But all the way back to the beginning again, this video is called Boost by Gear, and what we've just done is just tune the car and just put more and more and more boost in it. But I haven't gone off on a tangent, I promise. In order to do Boost by Gear, we first need to tune the maximum boost, and we need to know that when we target 18 pounds, we get 18. When we target 20, we get 20. Target 24, we get 24. So now what I can do is go back and have a bit of a think about what boost pressure I want where. So if I flick back to our tuning software, I'm going to come back out of our log viewing software, which I'm really enjoying using. Then I'm going to come up here, and this is where the magic's going to happen, and this is where we talk about boost per gear. So I'm going to go say here, and I'm going to tell this guy, Davo, if the intercooler water sprayer is off, he's going to get 18 pounds of boost pressure. That's all there is to it, and that's going to be our base pressure. That's the lowest power the car's going to make. If I now go to on, I'll flick on our intercooler water sprayer, and I'm going to say, okay, in fifth and in third, fourth, probably fourth, fifth, and sixth gear, 60% throttle onwards, 24 pounds of boost pressure. In third gear, 22 pounds. In first and second, 18 pounds. Then at zero throttle or 20% throttle, so the smallest throttle opening we can have, I'm going to target 18 pounds, just so that if he's part throttling 20 or 30% mid-corner, we're not going to be sort of spiking between 18 and 24 pounds as you're pedaling it, so it gives it a little bit more drivability. I'm going to come across and do something like this, and I'm going to go H for horizontal, so that'll horizontally linearize all of those values. And I'm going to end up with a table something like this. So if he's cruising at 40% throttle in third gear, he's going to get a target of 20 pounds of boost pressure. So you can see how that's working. You don't have to specifically set this up exactly the same. You can think of all the different conditions that work in your particular applications. It's a four-dimensional table. So we've got the X, Y, and the Z axes. The sky really is the limit in setting up your boost control strategy versus your throttle angle, versus your intercooler sprayer, versus your valet switch. You can put some rocket switches in. This is the way to get it done. It's a really, really nice, really simple solution, all contained within the engine management system, so you don't have to add any other complexity. If you've got a Haltech IC7 dash in the car, you can also display your trim position. You can also display your target boost pressure on the dash, so that when you flick your button on the dash, it'll tell you target 22, 24. If you get really excited, it'll say target 30, and that's when things start getting exciting. Remembering as well, we haven't gone through the whole mechanical boost control in this particular car. We did do a heap of that with that R35 video from the other week, and we'll put a link to that in the comments. So if you want to know more about power management and boost control strategies, flick over to that R35 video and take a look there as well. Well, we've come to an end today. I've had an absolute ball with the Evo 9. It really makes me feel at home in here. I absolutely love it. I'm going to have to organise with Davo that we might need to use this test mule for a few extra tests, maybe drive it home back and forward a few times just to, really get a feel for it. As always, thanks so much for watching. I know it's always a bit of technical content. I appreciate you sticking to the end. As always, my name's still Scott. Catch you next time.